No, sir.
Okay. Okay. Anyway, I will upload them into the website, and I will let you know about the link later on, so that you can go back to the previous lectures as well. Sorry. Okay, let me share the screen. Yeah, can you see the screen now?
Yes.
Okay. Okay, so we were talking about the microscope, right? Polarizing microscope, and I think this is a special kind of microscope, as you now know, because it has a some kind of polarizer, right? Polarizers and rotatable stage. Those are different features than what you normally observe in a biological microscope. So these components are important, right? Then we looked at the light and how the light travels, and we talked about the light travels as waves, and these waves are traveling from the source at various directions. I mean, the vibration directions, because these are particles. These are considered as particles. Therefore, they are having a vibration directions. I mean, a normal light is vibrating all around 360 degrees. That means in all the angles in the planar space, if you consider planar spaces along this line, all 360-degree angle directions, there will be vibration planes. So at some light waves will be vibrating in each and every direction around the 360. That means around a circle. But what happens when this light comes to the polarizing microscope? Because polarizing microscope, as we know, the petrological microscope, it contains a special component that is we call polarizer, and the purpose of polarizer is to reduce the light strength. Like we wear sunglasses. When we wear sunglasses, we have a polarizer, Polaroid film there. So likewise, we use a polarizer or the film, Polaroid film, to polarize the light. So then we can convert this light to be propagated along one direction only. I mean, they will be vibrating, of course, but they will be vibrating along a single direction, not in every direction. So all the other directions will be cut down by the polarizer, apart from the direction that it permits along the Polaroid, because the Polaroids contain some specific directions. Through that direction, vibrations can be passed through. So that's the mechanism of a polarizer. So all direction vibration light will be converted into monodirectional vibrated light. Okay. So these light vibration directions will be cut down. So when polarizer is inserted, that means in here in the microscope, you can see here there will be a polarizer. Okay. So exactly in this place, right, we have the polarizer. This is the device, the lower polarizer. So that will polarize. So I have denoted it here as the polarizer. So once this polarizer is inserted, this light vibrating in all directions will be converted into a single directional vibration. That means a beam, what we call a plane polarized light beam. So this is the direction in this polarizer, for example, it allows vibration along this direction only, right? So because this polarizer has that specific vibration direction, because that is a manufacturing feature, okay, along this direction only. So all the other directions like this direction or this direction, everything will be cut down. So anything parallel to this direction, that means from this initial light beam, the light rays which are vibrating along this direction will be permitted to pass through, right? So that goes as a reduced strength light beam, and what we call it's a plane polarized light. So uh, it can move through still, but only one direction. So light intensity decreases. And then what happens if we insert the second polarizer or the upper polarizer, because we have two polarizers. One is by default inserted, right? This lower polarizer, by default it is inserted. You can't remove unless you physically unscrew it and take it out, right? It's normally along the light ray path. But there is another one, that is the second one, which is fixed in the upper side of in the upper body part of the microscope, that is here, right? It's inserted here, but this one you can remove easily if needed. That means there is a small lever here, right? Small lever here. You can pull it or push it. If you want to remove the polarizer, sorry, if you want to insert it, you can push it. If you want to remove it, you can pull it out, right? So by default, normally we keep it as open. That means you have kept pushed it out, okay? You have pulled it out, so that there will be only one polarizer, the first one, the default, the already fixed one is there, right? But when we need, we will insert the second one, right? It's here. But the important feature here is the first polarizer is below the stage. First polarizer is below the stage. Here you can see below the stage means you put the sample on the stage, right? We put the sample of the thin section, rock slide, a very thin rock piece or a mineral piece or a gem piece even, we can put on the stage. And then when the light source is here, the bulb is here. So when the light passes through the polarizer, it carries only a plane polarized light, because it is passing through the lower polarizer and it enters to the sample and then moves to your eye, because this is the eyepiece, right? Through that only you can see the light which started from here and which enters into your eye. But if you insert the second polarizer, that means upper polarizer, then this light which is coming after the sample will pass through the second polarizer also, right? Then it will enter your eye, right? So there are different observations when you insert it and when you remove it, right? So that I think we have already discussed the last lecture, but still I will remind you again. So the first polarizer is this one, the lower polarizer. It polarizes the light in one direction, right? Along this direction only, because it's the its direction. Say this is west and east directions, right? It's just you can say any direction, but just for our convenience, we'll put it as east-west directions, like that. So this light goes through as plane polarized. So you know, up to the stage, right? Up to the stage and onto the sample. It enters to the sample. So before entering the sample, if there is nothing on the stage, this plane polarized light should come into your eye as plane polarized light beam. We call it PPL, okay, plane polarized light. So it should reach your eye and you should see some illumination because light is coming. If light is not coming, you will see total black here, right? But you will see some brightness because light is passing, right? So if that means from here, from this ocula or the eyepiece, you will see some brightness when the light is coming. If no light is there, you will see nothing here except for black, dark black color through these lenses. Okay, then we'll see what happens if we enter the second polarizer, the upper polarizer. So this is the upper polarizer. So we enter this upper polarizer, but this upper polarizer is made or manufactured in such a way that it's perpendicular, its vibration direction is perpendicular to the lower polarizer. So we had the lower polarizer perpendicular, the vibration direction as east-west, we said east-west. This one, the upper polarizer will have the 90-degree different vibration direction. That means north-south vibration direction. So basically you will have two perpendicular vibration directions in these two polarizers. So that means the first polarizer will allow only the light which is vibrating along the along the east-west direction to pass through, and the second polarizer allows only the light which is vibrating along northeast, north-south direction only, right? Perpendicular direction, because it's made that the vibration direction should be opposite to the first vibration direction. Okay, so now you see here the light is coming from here, right? Because the light source is on, so it passes through the first polarizer, and east-west vibrational light is coming and trying to enter the second polarizer. You see there is no sample, right? There is no sample in between. If you had a sample, it should come somewhere here. Okay, but now you don't see any sample here, only the light is coming. But we have inserted the upper polarizer. So this upper polarizer, you can just push in the microscope and you insert it. So then what happens? Your light vibration direction is here. It's vibrating in east-west direction, but the upper polarizer allows only light to pass which has a vibration direction of north-south. But what happened if this light enters? This has east-west vibration direction, so it will cut by this upper polarizer. So in case if you had some light coming along this vibration direction, then it will allow definitely to go through this one. But now at the moment there is no such light, so therefore you will not get any light out of this second polarizer. So what happens is from this ocula, from this eyepiece, there will be nothing coming out for your eye to see. So that means it is total black. So you will see total black. There is nothing coming out of this polarizer, second polarizer, right? So this is the principle behind these two polarizers to have in opposite directions, and this phenomena is very important in identification of minerals. So we will see how we use or we utilize this feature for identifying minerals, because the sample should come in between here, right? So sample should be placed here, somewhere here. Okay, so then what happens if you put a sample, then this incoming light will be going through the sample and then enter the second polarizer, right? So if the minerals can change the vibration direction somehow, and if they can produce any light ray which can be vibrating along this direction, then what will happen? You will have some light here, right? In any case, if the mineral, when you put the sample on the stage, can change the vibration direction of this east-west vibration direction, so that it will turn into some other vibration direction parallel to this direction. Okay, if some minerals can reorient, that means if this some of these minerals can reorient the light, then there will be a possibility for this second polarizer to transmit the light. In that case, instead of this black, you will see some bright colors here. Okay, so we'll see how that can happen and what will happen if a sample was placed there. Okay, right. So now we have put a sample inside, sample in between. That means on the stage there is a sample now. Now you have the sample, thin section is here. Okay, so you know these thin sections contain so many types of minerals, right? Quartz, feldspar, tourmaline, topaz, many types of garnet, many types of minerals. So their properties are different. And I think I mentioned last time that some of one category of mineral is called isotropic and the other category is called anisotropic. Probably you can remember. So these isotropic and anisotropic behavior causes us to pass some light through the second polarizer. That means this behavior is a feature that helps to reorient the light when the plane polarized light is coming through the sample, right? So some minerals are able to reorient the light. So reorient means already vibrate in direction like this will be changed. They will be reorient. They will be changing to other directions, like, for example, like this direction. Okay, so in that case, the light coming after the sample will be having some other directions, not only this direction, but also maybe some other directions like that, because the minerals oriented in this thin section will be in variable orientations. Therefore, they will not only orient along this direction, but also maybe some other directions also, right? So therefore, again, you will be having some form of a light which has various vibration directions, several vibration directions based on the mineral combinations you have inside this sample, right? It's more or less similar to the original situation, unpolarized situation, but actually this is not really unpolarized. What it did was the real polarized light was reoriented again into several directions, but it won't be the same light as here, right? It will be different, right? Because the beam is different, because already you have cut so much of vibration directions at the first polarizer. Therefore, it won't produce the same light as it was in the from the source, right? So, but anyway, it will be having multiple vibration directions, but out of those multiple vibration directions, only the direction which is parallel to the upper polarizer's vibration direction, that means this direction, right? That light will come out from the second polarizer and enters into your eye. So here, when it comes to your eye, you will see various colors, right? Here, you see the image, you can see green, orange, yellow, white, black, everything is there, right? It's because this light, this reoriented light was having various frequencies, various components, right? So those components will be having, for example, say like this. This is the vibration direction of the second polarizer. But in case if you had say like this direction, right? If you had a vibration like this, then it will be transmitting the vibration direction parallel to this line, okay? Because this is the vibration direction of the second polarizer. So therefore, from this light, the component, the amount of light, not the entire light will be coming, the component parallel to this vibration direction, that means this vibration direction here, will be entered like that, right? So if you have a angle here theta, right? So and say the strength of light is here F. So you will have a component called F cos theta, right? You don't need to take these things very seriously, but just remember the component which is parallel to the vibration direction of the second polarizer will be coming. So that is F cos theta mathematically. So you know the force uh, we resolve into two directions, perpendicular directions, cos theta and sin theta based on the theta angle, right? Uh, right. Similarly, the component which is parallel to this vibration direction will be passing through this second polarizer. So therefore, their strengths will be very different because it depends on this theta angle. Because some lights may be having a larger theta value, and some might be having smaller theta like that. So depending on that, you are getting various strengths, various frequencies. That's why you have a lot of colors here. So you should understand that this is not the real color that you have on your thin section. Okay, these are not the real color. Actually, these are some kind of artificial colors because of this reorientation. It's not the natural color of the mineral. If you want to see the natural color of the minerals, you have to see here. Exactly, you have to observe at this place when the light passing through the first polarizer only. Whenever I'm sorry, not here. Here you can just observe your eye here, okay, without inserting the second polarizer, right? So if you observe here, you will see the natural colors of the mineral because the entire light beam is passing through here. Okay, entire light beam is passing through, but it's only thing is it will be vibrated, it will be resolved into different vibration directions by the minerals themselves according to their isotropic and isotropic behavior. But anyway, the whole light is coming from the light source to the through the mineral to your eye. So therefore you will see the natural color. But here you are filtering it again, like kind of filtration, so that you will get not the real frequencies out from the second polarizer. So therefore you will see vivid colors here, not the exact natural color. So anyway, these different colors are a result of the second polarizer. We will discuss about this phenomena later on. Anyway, these colors are important. These different colors, green, yellow, black, like colors are also important for us for identification of minerals, because these colors, these each and every color is again a characteristic feature of a mineral. So therefore, to identify the mineral, distinguish the mineral from this green one to orange one, we have to use this color and some other properties. Okay, some other real color parameters, that means natural color parameters, we can observe here for mineral identification. But when you can't identify them because some minerals are giving same color, same natural color, so in that case you have to insert the second polarizer and see how this second after the second polarizer their behavior. Then you can change, you can understand. The first polarizer might give you the same colors of two minerals, but when you insert the second polarizer, those two minerals will be giving two colors. So in that case, you can distinguish those two minerals. So for that purpose, we use this second polarizer. So anyway, the light reaching your eye will be having a vivid color spectrum, because it passes some component, like here, some component through the second polarizer, not the entire beam which is available here. If you can see this entire beam coming out, then you will see again the natural colors, but that never happens because this is the vibration direction is this way. Okay, so this is how those two polarizers are working. Is it clear for you? Is it understandable?
Yes.
Okay, sir.
Okay, right. This is important when you can witness this when you do the practicals. Okay, so we will move. So the conclusion is that having these different colors after the second polarizer means some minerals after passing their sample stage, they can reorient the light. Okay, some minerals can reorient, some minerals cannot reorient. So those which you can reorient light will be showing various colors like these, say orange, purple, white, gray, like that. But there are some minerals which cannot reorient the light. Such minerals will be giving black colors. So if you can't reorient the light means you don't get light out of that mineral. For example, this mineral, it cannot reorient the light. So that means there will be no component to pass through the second polarizer from that particular portion of that mineral. But these minerals can reorient the light so that the second polarizer after passing, you will see some kind of a color. It is not the natural color, but still you will see a color. So that means such minerals are possible to reorient the color, whereas these black ones means they cannot reorient the light. So the take home point is some minerals can reorient the light, some minerals cannot when it passes to the upper polarizer. So this is another important observation. So some grains they remain dark. That means they cannot reorient the light. Okay, right. So when you can observe again when you rotate the stage. So once you see this image, you can rotate the stage. Okay, you can rotate the stage 160 degrees. You can rotate the stage. So if you rotate the stage and see your mineral behavior, for example, suppose you have one mineral here, right, which could reorient the light. That means it should give a color, right? It should one of the minerals like here, for example this one, say you are not rotating it. So then what happens? So every 90 degree when you rotate the stage, every 90 degree, right? So from this point up to this point, so this is 90 degree. Okay, you rotate the stage, what will happen? It will become dark. The previous colored mineral, say green color mineral, which becomes dark. Again, you rotate it another 90 degree. Then it becomes bright, that previous color. Again, 90 degree. It becomes black. Again, 90 degree. It becomes bright. So that means every 90 degree, when you rotate the stage, so 4 times, that mineral, even those are having these brighter colors, will be going black like this, right? But not always, every 90 degree only, right? So see, so they, when you rotate, that's why we need this rotatable stage for petrographic observations. Otherwise we cannot observe this particular feature. But if you see that black mineral like this one, right, like this one, if you rotate the stage, what will happen? So let's see such a mineral. Okay, so we have such mineral here, black one, and we start rotating the stage. 90 degree rotated, another 90 degree rotated, another 90 degree, another 90 degree, another 90 degree. So still they remain black. All the time they remain black. Okay, so that's why this black mineral, that feature is also important for us. When you rotate the stage, always if the mineral is staying black, that means that mineral cannot reorient the light. So those who cannot reorient the light, we call isotropic minerals. We call isotropic minerals for those which cannot reorient the light. That means they remain dark always when you rotate the stage. But the previous one, the other type, when you rotate every 90 degree only, they go black, but other times they will be brighter, right? So such minerals we call anisotropic minerals, and the other ones isotropic minerals. So these are the two types of minerals we have from those who can reorient, the main categories of minerals that we can find after inserting the second polarizer, right? So some minerals can reorient the light and the other ones cannot reorient the light, right? So those who can reorient the light, we call anisotropic minerals, and those who cannot reorient the light, we call isotropic minerals. So the first two main categories of minerals are this one. Actually, this is optical categories, okay, not physical category. Optical category, isotropic minerals and anisotropic minerals. So this is another very important feature. So the generalization we had before was there are two types of minerals, isotropic and anisotropic. And for example, garnet. Garnet is an isotropic mineral. That means once you, if you are observing garnet on a section, through the petrological microscope, and if you insert the second polarizer, the upper polarizer, even though you rotate the stage, always garnet will be black. You can't see any color change. But other minerals like pyroxene, olivine, feldspar, quartz, they show different colors even after inserting the second polarizer, so that they are anisotropic minerals, right? So these two categories are there in optical mineralogy, isotropic minerals and anisotropic minerals. And from these anisotropic minerals, we have another two subcategories. There are there are some special directions where they cannot reorient the light. For example, in the previous case, when you rotate the stage, see, in some directions it becomes black, right? Anisotropic minerals. So it becomes black means when the mineral is in this point, this direction, it cannot reorient the light. So that means this is a special direction for that mineral. Again, another direction is there, right? So actually there are one or two such directions for these minerals. Although you have 4 times, that means plus minus opposite directions. That's why you had four directions. But there are some directions where you one or two directions based on the mineral group category where they cannot reorient the light. That means they remain black as we observed in after the second polarizer. So these two special directions are called optic axis directions. Okay, optic axis. It's difficult for me to write here, but we will come to that later on. Optic axis. Okay, optic axis. So along the optic axis, they cannot reorient the light, so they remain dark. So from these anisotropic minerals, some minerals have one special such direction, right? One such direction. And if they have only one direction, we call it uniaxial. And some minerals will have two such special directions, that is called biaxial. Okay, so out of anisotropic minerals, we will have one direction where you see only one such direction which cannot reorient the light. But some minerals have two such directions where they can reorient the light. So all the way you rotate the mineral in 360 direction, 4 times will be giving dark appearance for those minerals which have two specific directions. Other minerals will have only two black directions, right? In the previous example, you saw it in four quadrants, right? So that means it's a feature of a biaxial mineral. So like that, there are two such categories out of the anisotropic minerals also. We call them uniaxial and biaxial. So this specific direction is called the optic axis direction. So uniaxial means for uniaxial minerals, they have only optic axis one optic axis only. For biaxial minerals, they have two optic axes. Okay. So because they have two special directions means those two directions are called optic axis directions. But for uniaxial minerals, only one direction. So that means they have only one optic axis. Actually, this is not a physical axis. It's a optical orientation only. So it's an imaginary direction in a crystal. Okay. So when you have the crystal, real crystal shape, you have different axes, A, B, C, crystallographic axis, right? So those are, you can locate physically them in the mineral, but these optical axis, they are just some imaginary axis only, which you can observe only with the microscope too, not by normal physical observations. Okay. So now we know anisotropic minerals can resolve light into two plane polarized components, and they travel different. I said when it say the first polarizer here, and it comes, the light passes through as the plane polarized light, and then it enters the mineral grain, that means the sample, and it will reorient the light. So I showed you a bunch of light beams in the previous slide. It's because, see here, because you have a collection of minerals. There are many minerals here. So you will have different light at different angles, like I said here, theta angles, different theta angles. So therefore, you get a bunch of light beam again out from the sample, and it will come out as vivid colors. But if you take just one mineral, it will you will see they split the light. So sorry, I forgot to mention you about the splitting. So this is we call splitting of the light, right? Because until this point we have one direction, right? One plane. But when it comes out, it will be splitting into various planes, right? Depending on the mineral collection. But if you had only one mineral there, right, just one mineral there, the plane polarized light comes here, and you will see only two splitting directions, right? You will see only two splitting directions like that. But now here you have a combination of minerals, so therefore there will be so many splittings taking place like this. Okay, because so many minerals are there, so they are giving various theta angles. So that's why you see a bunch of beam here, rays here. Okay, so when the light hits, the plane polarized light hits an anisotropic mineral, right? In an anisotropic mineral grain, this is mineral grain. So suppose this is an anisotropic mineral grain, so it should be able to reorient the light. So it should actually give you two oriented directions, right? Two directions. But if you had several minerals here, right? If you had many minerals here, then you will see another kind of bunch of reoriented lights. Say 4 minerals were there will be 2 into 4 uh, light beams orientations. Okay, but here we have only one mineral, therefore you are supposed to have only two splitting directions. Remember, these two splitting directions are always perpendicular to each other. Okay, so the vibration direction. So if one vibration direction is this way, the other vibration direction will be like this. Right? They are planes, vibration planes are perpendicular to each other. Okay, so that means they travel like this vibration direction and opposite vibration direction like that. Okay, sorry, not traveling direction, this is vibration direction, and you have the light beam traveling same direction, right? Because it is aiming at your eye, right? To the eyepiece, ocula, right? For the microscope. It doesn't go here and there, everywhere. It doesn't go here and there. But only thing is the vibration direction is perpendicular, two directions. So that means this vibration direction, this light beam will be passing like this, okay? Up to your eye, here, your eye, or the ocula. Okay, two vibration directions. The splitted light ray will be in vibrating in two directions. So we call one ray is slow ray, the other ray is fast ray, because their frequency is different. They have different frequencies. So one ray is lagging behind the other one. Once as soon as it goes out from the mineral, right, they go into velocities, right? They go into velocities. That's the that is dependent on the velocity is dependent on the mineral grain, the property of the mineral grain, and also the thickness of this mineral grain. So that is also very important. We will talk about that later on, but just keep in mind that this thickness is also very important to decide this uh, velocity. Okay, so that means when the first ray, say this orange one, gets out from the mineral and it starts propagating, but by that time this yellow splitted ray has not started its way, right? So but say it goes some way like that, then this yellow one will be also coming out and uh, going after that. So that means it's like two trains starting from the same station, right? One is starting first and the other one is starting late, right? So there will be a lagging behind, right, between these two at any given time, right? So this lagging behind, sorry, we call as delta. That is also important, right? So we will come to that later on. We denote this thickness as d. Just keep in mind, right? This lagging distance and also this thickness of this mineral grain. Those two are important on deciding these velocities of these two rays. So since one ray is coming out faster, we call it fast ray. The other one is coming late, so we call it slow ray. Right? These fast ray and slow ray are vibrating in perpendicular to each other, but they are moving along one direction, right? Because it is going from the sample to the eye uh, or the upper uh, upper whatever upper polarizer, right? Through passing through the upper polarizer, because upper polarizer is somewhere here, right? If you have the upper polarizer, then it will enter the upper polarizer, and then meaning upper polarizer is here, and then it will enter your eye. Okay, so if you had inserted the upper polarizer, then it will pass through, otherwise it will just coming directly after the sample, right? So this is the splitting of two lights having two different velocities. Okay, so this is what we call the two components, splitted two components after the mineral grain. But essentially this mineral should be an what kind of mineral? Anisotropic mineral, right? And it should be an anisotropic mineral. Otherwise they will not split the light, because they cannot split the light. They cannot reorient, right? This is the reorientation, two directions. Okay. So when they reach the upper polarizer, you see the rays will have uh, different velocities and different frequencies, and then it enters the upper polarizer and it will be giving out different colors. So that's why we saw vivid colors when it enters there. Okay, so that's why we see new colors. Actually, it is not the real color of this mineral. That's why I mentioned it's new color, right? It's a new artificial kind of color It's like rainbow color, just because of this splitting. And then after the polarizer, second polarizer, they will be resolved into that direction, that f cos theta component only coming out, right? So that's why they cannot give you the real color of that particular mineral. Okay, right, it is coming out now. And we based on these features, we divided the minerals into two categories, isotropic and anisotropic minerals. So always this isometric system behave as isotropic minerals. Isometric system means cubic system. Okay, crystallography, remember, cubic system. So this cubic system behave as isotropic minerals. So that means they cannot reorient the light, right? Because they are all the crystallographic axes are equal. And anisotropic minerals, we told that they have two categories, uniaxial and biaxial, two categories. These are anisotropic minerals. So they can be all the other crystallography, other crystal forms, but uniaxial becomes these hexagonal, trigonal, and tetragonal. So they are only behaving as uniaxial minerals, but the other ones, orthorhombic, monoclinic, and triclinic, they behave biaxial behavior. So the uniaxial means they have only one reorientation direction. They have only one optic axis, right? They have only one optic axis, but they have, the other group has two optic axes, right? These hexagonal, trigonal, and tetragonal minerals, their axes are equal and perpendicular to the c-axis. C-axis is the longer axis, right? All the other axes are equal, right? Other axis like this, you have several axes, they are equal, but perpendicular to the c-axis. And in orthorhombic and monoclinic, triclinic system, they are not perpendicular. They have different orientations, like some inclined, not 90 degree, right? So like this. So they have different sizes also. These axes are also not equal, right? So they have two optic axes because of their nature of the nature of this physical habit of having different crystallographic axes. So remember, we have two basic categories as isotropic and anisotropic, and the anisotropic can be divided into further two, that is uniaxial and biaxial, okay, based on their presence of optic axis, number of optic axis, one optic axis or two optic axis. So optic axis means the directions along which the light cannot be reoriented in anisotropic minerals. Okay. Right. So this is the crystal systems I think you have learned. And also, have you seen these samples in the lab already, the models?
Yes.
Have you seen this
Yes,
sample?
sir.
Sorry, have you?
Yes, we have seen it
Okay,
during
okay.
crystallograph practical.
Right, good. So you know about the crystal axis now. So cubic, tetragonal, hexagonal, orthorhombic, monoclinic, triclinic. So they have different situations, and so along which you have different orientation of light. So natural crystals will be like this, right? These are the natural crystals actually. If you are lucky to see them formed in euhedral form, we call euhedral for those minerals which have crystallized in good shapes, in good crystal phases, showing good crystal phases like this, right? If you see them in the nature. But most of the time you see them in anhydral forms. Anhydral means you don't see good crystal phases most of the cases, but you can find good crystal phases in some situations. maybe one half you are having good phases, but the other half maybe not having good phases. So in that case, you can call them subhedral. So the three physical forms are there: euhedral, anhedral, and subhedral. Euhedral means all the crystal is having very good crystal phases. Anhedral means no crystal shapes can be recognized, and subhedral means partially you can recognize crystal phases developed better. And some natural examples you can see here, right? So this is an anhedral crystal, right? More or less having the perfect crystal shape, and this also, right? And maybe this one also you can call, but other ones are like subhedral. They are not showing the perfect shape, but maybe this one is showing fluorite, but the other ones might not be showing the proper shape perfectly. Okay. So anyway, so this is the crystal system that you can observe in the nature. And based on these features, your observations under the polarizing microscope will be different. So that's why we are able to identify these minerals using the optical microscope. Sometimes we can identify them just by inserting, just by the plane polarized light. That means without the upper polarizer. But some minerals we cannot identify without the upper polarizer. You have to insert the upper polarizer and see the those that beautiful colors. I mean, not natural colors, but the vivid colors that you see. Based on that, you can decide what mineral it is. So we will come to that later. Right. So anything unclear up to that point about these categories? Okay, if not, we will proceed. So we will see some basic properties, mineral properties. The first two basic properties we call the color and pleochroism. Okay, the color is the natural color that we want to see. We can see the natural color only in PPL. Okay, that means without inserting the upper polarizer. So only the lower polarizer will give you the correct color, because I said already that when the light comes to the upper polarizer, it will reorient, and a component only will be passing through that, and it will give you a kind of distorted color. That's why you get some vivid color, which is not the real color. Okay. So some of the minerals that you saw before, like in vivid colors, like rainbow colors, their natural color is like this, right? This is the natural color, right? This is hornblende, for example. Okay, hornblende. This is the natural color, and this color is observable only under the plane polarized light, right? So with the light type, it might be changing the strength also, but still kind of you can easily identify them when you get used to these minerals, right? Your eye should be get familiar with these colors for each of those minerals by observing many samples. Then you can identify any unknown sample if this particular mineral is present there, right? Right. So then the other feature is the pleochroism. So pleochroism means when you rotate the stage under the PPL. So previously we saw the rotation of the stage under the second polarizer also inserted. Okay. But now we are going to rotate the stage with this lower polarizer only, the first polarizer only. That means under the PPL, we rotate the stage. So then what happens? You can see here one mineral here showing more stronger greenish color than this one. But actually both of these minerals are same mineral, that is hornblende. Okay, but now you saw two colors here. But I said this is the kind of natural color also, right? But when you rotate the stage, the strength of that color changes. It's because this PPL light beam, which is coming from after the plane polarizer of the microscope, when it reaches the sample on the stage, right here, the sample on the stage, when you rotate the stage, what happens is the amount of light absorbed by this sample will be differential. They have different amounts of light absorbing when it reaches the mineral, because these minerals are having different crystallographic orientations. So therefore, when you rotate the sample based on this crystallographic orientation, because you know there are different directions, crystal directions. So when you rotate this crystal into another direction, maybe it's like that in that case. So your original features will be lying like that probably. In that case, the amount of light absorbed at here is different from the amount of light absorbed at here. Okay, so therefore they will be giving you a different, slightly different color. Okay, sometimes this color might be entirely different from the original color. I mean, this green might be changing to purple light. Right? There are such situations also. That depends, all depends on the mineral property. Mineral, that's why it is regarded as a special feature for that particular mineral to identify. For example, pyroxene. If this was a pyroxene, you will see when you rotate the stage, light greenish pyroxene like here, like this color will be changing to purple color. So that is a special feature for pyroxene. So we use that special feature to identify pyroxene because no other mineral is changing like that. So we can distinguish that from hornblende easily. Okay. So like that, this special feature we can use to identify, distinguish the minerals, and that feature we call pleochroism. Okay. Pleochroism, the differential absorption of light, the amounts of absorption of light is called the pleochroism. So for example, for hornblende, it's pleochroic. We say pleochroic means it changes color when you rotate the stage. So if some minerals, there are minerals which don't change the color even when you rotate the stage. So that, then we call them non-pleochroic minerals. But most of the cases, hornblende, pyroxene, olivine like minerals, they are pleochroic. Okay, so that means they change the color when you rotate the stage. This is important for colored minerals only. For colorless minerals, for example, plagioclase. Plagioclase is a colorless mineral, and also quartz is a colorless mineral. So this pleochroism feature you can't use to identify them, because even you rotate the stage, you will see nothing. It's just colorless. Okay, so therefore this pleochroism is important for colored minerals rather than colorless minerals. So when you rotate the stage, and even here from first image to the second image, you can see this hornblende grain has become dark, a little bit dark green, yeah, like that. Okay, so when you rotate, you will see they are changing their colors. See, the strength is different, color strength is different. So this is what you call the pleochroism. So these two features are very basic features, two features that we use for mineral identification. So for example, biotite, hornblende, olivine, not olivine, olivine is mostly colorless. Pyroxene, both clinopyroxene and orthopyroxene, CPX and OPX. Diopside, those are pyroxenes. Pigeonite, augite, olivine, that means peridot, olivine. Sorry, olivine you can't, again, sorry, use this particular feature. But pyroxene, hornblende, like, yeah, antigorite, and what else? Yeah, there are many anyway. You can use this feature to identify. You can see them in the lab. There will be a lot of examples with different samples. You will see them physically there. So color and pleochroism is important for us to identify the minerals. So anyway, The refractive in the other feature is refractive index. That is also important, but of course it is nothing you can find from. I mean, you can observe from the. I mean, you cannot directly uh, measure the uh, measure the refractive index just by the microscope, but the features you see through the microscope can be used to calculate the refractive index in some cases, right? That will be given you as an exercise probably at the practical class. But anyway, when a light ray enters from one medium to another, for example, if this is air and if this is water, okay, what happens to that light beam? Instead of going it directly like that, right, it won't go straight, right? So light beam is straight, but once you have a new medium, this is air and this is water. So water is a new medium for this light beam, which is coming from air. So it doesn't go directly, and what happens is it turns. Okay, it turns, giving some angle here to the surface, changing its direction. This is what you call the refraction. This property we call the refraction. So if this happens, this change, if you draw some line here, if you draw a line perpendicular to this surface, right? We you can see this the new beam, new ray, which has turned towards this line, this perpendicular line, right? So equally, if you draw another line here, and you see here what has happened to the beam, it has turned away from that line, right? That means this angle is larger and this angle is smaller. Okay, so it happens when the refractive index differences are like here. So in the second medium where into which the light beam enters, if the refractive index is larger, then you will see it's turning to a smaller angle towards the perpendicular to the surface. But if the refractive angle is smaller, that means opposite, from water to air. If the ray is coming, if this is water and if this is air, so it should be opposite. Okay, so then the ray will be changing or deviated in a larger angle. So this is the refractive property of light beams, right? This is normal uh, phenomena. So anyway, we call it refraction. And of course, because of refraction, there will be a change in velocity also, right? There will be a change in velocity. So that's why actually you had this light ray splitting into two uh, uh, rays as fast ray and slow ray. Remember, we talked about fast ray and slow ray here. See, that is all dependent on the refractive index. So actually, that is what it determines. So that's why they have two velocities. The refractive index is different. So it is important. So isotropic minerals, that means like garnet like minerals which cannot reorient the light. Isotropic minerals, you remember, which cannot reorient the light, will have one refractive index all the way around any direction. If the light passes through that mineral, it will be going at a single angle change. No refraction, I mean no multiple refraction is taking place. So there will be only one refractive index, right? Refractive index is determined by this one, velocities, right? Change of velocities. And for uniaxial minerals, there will be two refractive indexes because they have two directions for the splitting of light and the behavior that makes this change in refractive index. But biaxial minerals will have only three refractive indexes based on their light passing through the mineral. So anyway, you will, I think you are not going to have complications, but you will observe some different minerals which will have, because for determine this refractive index, there are some complicated procedure utilized with the optical microscope also. It's possible. We call optic figure, right? That is not used, I mean, it is not, it's just for the mineralogist that is used mostly. So anyway, so these are observable indirectly for us with two optical parameters. Like previously, we talked about color and what is piochroism. Like that, we are seeing some other properties, two indirect properties based on the refractive index as relief and birefringence. So we will see what these two special features in a thin section, right? So relief. So one feature is relief. So it is actually the relative difference between the two refractive indexes. So if you have two refractive indexes, so that means N1 minus N2. Okay, if you have two refractive indexes, then you can have the difference. In biaxial cases, I said that there are three refractive indexes. So that means N1, N2, and N3. So there will be several values you can find, like here N1 minus N2 and N2 minus N1 minus N3 N1 minus N3, and also another one you will have N2 minus N3. Okay, so like that you can have a range of values for this refractive index for biaxial minerals, but for uniaxial minerals you have one range, only one range. Here for biaxial minerals you have three range. That means their refractive index difference is large difference will be there. Okay, so that reflects us another property which we call relief. Actually relief, normally what we call relief, normally in normal, I mean in plain language, we call mountainous areas. For example, Kandy, it's having a lot of mountains, right? So we call them such areas as high relief areas because you have a lot of mountains. Say Gampaha, Colombo, like there will be no big mountains. So there you have low relief areas, right? That means it's like when you consider some level, right? How high or how embossed or how prominent that particular feature is visible, that is relief. So for minerals also you have similar property which we call the relief. For example, you have one mineral here and another mineral here and another mineral here. Okay, so it's like if you see a kind of a cross section, and you will see very planar shape here, but a little bit higher relief in the second mineral, and the other again you have low relief, and the other one will have another kind of relief. So you are seeing some high relief areas. So you are seeing some high relief areas. Okay, so you are seeing some high relief areas based on these three mineral distribution. Even here same, you have high relief area, and low relief area here, right? These are low relief areas. So you can I think you can easily see even this photograph. This is photomicrograph. That means a photograph taken from a the optical microscope, right? So such things we call photomicrographs. This relief is determined by relative differences in refractive index. Actually, you have to note that this relative difference is not between intermineral relative difference in refractive index. For example, this is plagioclase and this is olivine, but this relief, this high relief seen by olivine is not a matter of plagioclase and olivine difference, right? It's exactly a matter of there is a glue used here. We are using a glue on top of this glass slide, right? And on top of that only you have this rock piece. Okay, you have a rock piece on top of that. So when you have a rock here, in between what you have a rock here, the slide here, and you have a glass, and this is the, say this is the mineral. So you have a glass here, and on top of the glass, what you have, a glue. On top of that only the sample is pasted, right? This is a permanent glue, and then you have the mineral. So these two will give you this relative difference, the refractive index between this glue, because this is transparent glue. This is a special glue used for mineral pasting minerals. You can't use any glue. There is a reason for that also. I will explain that later on. That glue is laid on top of the glass, and on that you have the mineral. So you have mineral, the light is passing through that. Light passes first through the glass, and then in fact through what, the glue, right? Then after that only it enters the mineral. Okay, so this n minus n2 means difference between the mineral refractive index and the difference between the glue refractive index, right? Actually, when we select these glues, because we need a glue, otherwise you can't hold the sample on the glass. So therefore, but if you use a kind of a multi-bond or something, it is too thick, and the light cannot properly penetrate through that, and also not visible the feature. Therefore, there should be a very, very transparent type of a glue. Okay, so it should be like almost like identical to the glass, right? Even though you applied it on the glass, you might not see difference. It should look like glass, even though you applied it a layer like, right? So therefore, this special glue is manufactured in such a way that it has the same refractive index as the glass, right? 1.5. Okay, the refractive index of glass is 1.5. So this glue will also have the 1.5 refractive index. So there will be no harm for the light passing through that glue. It will behave like the glass itself, right? So in fact, this is very, very crucial in selecting this glue, because that's why you have a very prescribed glues to use this one. Otherwise, the light ray will be distorted, right? If it is distorted and come to the eyepiece or the ocular, then you will realize some strange color, right? So that will make you difficult in identifying minerals. So therefore, everybody must see the same color. For example, if you observe olivine in Sri Lanka, and another person who is observing olivine in America should see the same color after the second polarizer inserted in. Otherwise, we can't have a common consensus, right? Having this particular color, right? Both of us should see the same. Otherwise, we can't say that this is olivine. Okay, so that's why all these standards are there, right? Even the thin section has a special thickness. Otherwise, it will change these properties. That's why in the previous slide, I mentioned about the thickness of that mineral is important. Okay, there is a reason for that. So I will explain it later on. So anyway, this relative difference in refractive index will give you the the amount of relief that you observe. Okay, so this high relief, low relief, moderate relief, like that you can estimate, right? So normally we estimate this relief, right, whether it is high relief or low relief, like that. So here you can see this plagioclase is very plain, like it's very low lying. It's almost on the glass, because this is on top of the glass, right? This mineral sample is pasted on the glass, so it's almost the glass level plagioclase. So we call it low relief. But olivine, you can see it's lying little bit higher than the plagioclase level, right? So we call it high relief. So like that, there you can determine the relief. So some minerals are showing standing very high, like garnet, for example. It will show more than this, more than olivine, standing up uh, relative to the glass level. So anyway, this relief is also important because we define this relief and we categorize in manuals, in books. Garnet is having high relief, this color, this like that, the other features, different features. When you lift out, the relief will also be a one such feature, whether high, low, or moderate, like that, right? So based on that, we can also recognize or distinguish the minerals, because some minerals will be having the same color but they are having a different relief. So in that case, you can easily use a relief to distinguish those two minerals. For example, fluorite and garnet, both are isotropic, right? So that means even if you enter the second polarizer to see any color difference is there, you will never see color difference because both are black, both are isotropic. But the fluorite is very high relief than garnet, right? Even garnet seconds to fluorite, right? So in that case, you can identify that as fluorite. So like that, for distinguishing these features, it's important. Okay. So these are some common values. For example, olivine is having refractive index differences in a range like this. Okay. And plagioclase, you see, it's very close to glass value, 1.53, 1.57, right? It's very almost 1.5. That is very close to the glass or the glue value. Glue we call epoxy, right? Epoxy is the name of the glue. I mean, it's a common name for the epoxy, but for the epoxy that we use for pasting these samples, we call petropoxy. It's a kind of a commercial name. It is giving this 1.54 refractive index, which is identical to the glass, almost glass. So that's why this plagioclase is showing low relief, whereas olivine is showing high relief because the relative difference is high. And please enter your name and number in the chat box, right, for attendance. Okay, so this is relief difference, and see some example here how the relief is determined, as I mentioned. So you saw the difference in refractive index, right? So that is reflected here also. Okay, right. So in the middle example here, this one, you can see the sample refractive index is same as the epoxy, right? So that means in the previous phenomena, we had a surface and one ray is coming, and if the refractive index is larger, it goes like that, right? Refraction takes place. But if the refractive index is same for those two medium, what will happen? the okay, sorry, let's take the rays coming like that. Okay, and suppose two refractive indexes are same, here and here both are same. In that case, there will be no refraction taking place, right? It will not change, it will go straight like that, right? It will go straight without any change, right? So if the refractive index is same, then it will try to go straight, so that you will have a very low relief, low or no relief, right? It's not low only, even no relief. If the difference is very tiny here, you will have a low relief like plagioclase. Okay, so plagioclase you had only very tiny difference, see 1.53 and 1.54, very small difference, right? It can be variable up to 0.57, but see it's a very close. And if it is if it is high, you have the sample high relief, high refractive index. So that means it behave like this, behave in this manner, right? So the light will be bending, and when it goes out, it will be having another angle, so that it appears that this mineral is uh, higher than the normal level. That's why this relief is coming up. And in some cases, you can have the opposite situation also. So that is not a common situation. There are epoxies having very large, I mean, this difference should be very large in that situation. But here, to give a large relief, very high relief, this difference must be bigger, very big, right? Otherwise, it will give you some small relief. If it is very large, then you will have large relief difference. Otherwise, some small relief difference, like that, right? It depends on the relative difference anyway. So if the epoxy is very large than the sample, so this is normally in natural cases, we don't see much, right? In that case, it's like the relief will be also high, but it looks like this, right? It will be high relief, but it's like something like how can I say, concave like appearance will be there. Concave like appearance will be there. Okay, concave like appearance will be there. So this time we call it negative relief, high relief but negative. Okay, so this is not very common in minerals, but these two cases will be observing you in the uh, in the in the practical classes. Okay, so this is a important feature anyway, so we have to keep in mind that this is important. This is again some example. You can see relief differences. For example, garnet, you can see it's high lying compared to the glass. This is the glass, right, on the epoxy. And quartz here, see, nothing. It's this is the quartz. It's almost nothing, right? I mean, no relief. And autoclase is also showing very slight, very low relief, right? So like that, fluorite, see, and apatite and beryl, right? So these will be showing different relief styles. So all these things you can observe in the class. Okay, right. So remember these minerals. We have categorized them isotropic and anisotropic. And anisotropic minerals we again categorize as biaxial, uniaxial, like that. So you can remember the crystal systems as well. And in such some minerals, since this since this splitting of rays is happening, right? Two vibration directions happening. These two vibrations directions, but of course the ray is going in one direction, right? Remember, the ray is going in one direction. That's why it is coming to your eye. Right? Otherwise, one ray will not come into your eye if they are going in two directions. If you put the calcite crystal, on top of a paper with some writing is there, right? You will see two images. See inside here, you can see two writing. I mean, cal twice. Why is that? That's because of those two rays, fast ray and slow ray, right? Both rays are coming out. right? Both rays are coming out, giving two images, as if they are two rays. Okay, so actually it is not two rays, it's a single beam coming out, but two velocity difference is there. So one ray is lagging behind the other. So it appears like, for us, it appears like coming as in two rays. So therefore, you have two images produced. So we call it double refraction. Okay, so this is a uh, very important feature for anisotropic minerals, and especially these groups, except for isometric group, because isometric is isotropic mineral, so it does not make any double refraction. All these crystal group will make this double refraction, anisotropic minerals. Okay, so this is an example given by calcite. Okay, so this is regarding the main main three features that we use based on this light behavior. For example, color, pleochroism, relief. So these three are very important features. Okay, the birefringence, which I will explain at the next class, because it's a kind of a detailed explanation. So I have to take the class to another 1 hour at least to go to that. But for the time being, we will stop here because at the point of double refraction, I want to stop today the class. But at the next class, I will explain the birefringence because it takes a little bit longer. Okay, so please keep in mind that we have to remember these features practically. Otherwise, we cannot identify them, right? To distinguish them, these are very important. So has everyone entered your name? Please enter. There are 9 people, but I see only few of you have entered your name. Please put your name in the chat box. And do you have any questions?
Yes, if you don't mind, can you share the recording? Actually, I missed few parts in the beginning.
Yeah.
So
I will
is it
most
possible to
probably
share?
share it tomorrow. Okay.
Okay, so no problems. So
Yeah.
because this part will be very important when you do the practicals, right, sir?
Yeah. In the previous classes also, I will share you. Maybe through a
Yes, sir.
YouTube link, I will share you so that you all can subscribe and get whenever I upload. Okay.
Okay,
There
so
are
that
some
will be
other
great,
extra
sir.
classes
Thank
also
you.
in that particular site, but no harm, you can access for your extra reading. No problem.
Okay, sir. Thank you, sir.
Okay. So we will stop here. So any other questions? Okay, if no questions, so let me stop here now. So we will meet another time to continue. Several classes, I think we have to do at least 2 more before you start practicals. Okay, right. Thank you.
Thank you, sir.
Thank you, sir.
Thank you very much, sir.
Okay.